Welcome, everyone, and thank you for joining us. I am Krista McNamara, Editorial Director with PTEN and Motor Age magazines. We're here this evening to tackle vehicle networks and diagnostics. Snap-on trainer Jason Gabrenas is going to lead us in a look at vehicle network structure and operation with a focus on testing strategies for CAN and FlexRay networks. Throughout the presentation, please submit your questions using the Q&A tab at the bottom of your screen. Jason will then tackle as many as time allows. Again, on behalf of Motor Age, PTEN, and Snap-on, thank you for tuning in. Jason, over to you.
Thank you very much, Krista. Hello, everyone. Welcome. Thank you for joining us for this evening, or well, I guess whatever time it is, wherever you are out in the world. As Krista said, my name is Jason Gabrenas. I'm one of Snap-on's National Diagnostic Technical Trainers. Been in the training department the last 8 years, traveling around North America, helping techs and shop owners get the most out of their diagnostic equipment. Before I did that, I was a couple years as a sales rep with diagnostic sales rep with Snap-on, had 30 different Snap-on franchisees I worked with, as well as the customers that they serviced in order to help everyone get the most out of their diagnostic needs. Before that, it was 8 years at Subaru. So I became, I guess, over time, a diagnostic tech at a Subaru dealership. So that's where I got all the drivability problems, the intermittent problems, the weird wiring problems that would show up on those cars. That's really where I cut my diagnostic teeth, so to say. And then before that, a bunch of other miscellaneous wrenching jobs. Been a little over 25 years under hood experience for me. So our topic at hand is data bus testing and diagnosis. Now, we do have multiple types of networks out there in the automotive world, right? All the way back from the 80s all the way through today. So we have the low speed networks, our J1850 variable pulse width and pulse width modulated. We also have the K-line, which is also used mainly in Asian vehicles. We have LIN bus, so local interconnect network. And then we have CAN, which is where we're going to spend a lot of our time talking about CAN, because that is one of the more prevalent network types out there in the world today. Also FlexRay, they're very related. And then we also have MOST, which is media-oriented systems transport. And then we also have the new kid on the block, Ethernet, or you may have heard it as DOIP or diagnostics for IP. So to get grounded, to get started, let's just talk about networks in general. So a network is a system that utilizes information from all available resources. So we think about all the nodes connected to this network. It's going to use information from all of them. If you think about maybe the network in your house, so you could print on your printer that's connected to your network from your phone. Then you can be sitting on the couch and the printer could be in the other room on the other side of the house. That's your network altogether. Now, if we think about different types of networks you may already be familiar with, well, that first one, that LAN, local area network. So that is like the Wi-Fi network at your house or at your shop. Now, all of these locally connected machines, computers, tablets, phones, printers, what have you, that is your local area network. And then we have a WAN, or wide area network. So that is going to be multiple LANs connected together. So that's just a really fancy way of describing what the internet is, right? It's a bunch of smaller networks connected over a wider area. And then if we think about how networks apply to the automotive industry, we have CAN, which stands for controller area network. And then we have LIN, which stands for local interconnect network. You may have heard that referred to as LIN bus. And then diagnostics over IP, DOIP, that is your new kid on the block, as they say, right? So with networks, how they work is what we call a voltage differential, right? So we have a high side and a low side, right? So we have, in this case, we're looking at a LIN bus signal. So LIN bus, what that works off is a 12-volt differential. So we have a high side and a low side. In this case, this LIN bus happens to run at alternator voltage. So we have a high side of 13.35 volts. And then on the low side, we have a 0.91 volts. So that gives us a difference of 12.44 volts, or a 12-volt differential high to low. So depending on how the network is set up, it might have a different differential. Some have 7-volt difference. Some will have a 5-volt difference. When it comes to CAN, it's about a 2.5 volt difference is what we're going to see. So when we talk about CAN, we talk about the mainly high-speed CAN. There's also medium-speed CAN, low-speed CAN, and there's actually a higher-speed CAN than what we're talking about here as well. So CAN consists of two twisted wires and with a transmission rate of 100 to 500 kilobits per second. So when you get down in that 100 kilobit range, you're talking about maybe a low speed CAN. 250 kilobits is probably about a mid-speed CAN. 500 kilobits is your higher speed CAN. And then there's even faster CAN that's out there as well that's come down the pipe in recent years, and that gets up to 1 megabit per second. Now, when we talk about that voltage differential, as I said earlier, CAN uses a 2 to 2.5 volt differential, and we'll see a lot of these patterns as we go through the evening here. Now, one signal circuit is going to be identified as CAN high, and the other signal circuit is identified as CAN low. So I have a high and a low. At each end of the data bus, there's a 120 ohm termination resistor between the CAN high and the CAN low circuits. So as we said, it's twisted pair. And then at the end of the line, wherever those circuits terminate, is going to be a 120 ohm resistor. Now, sometimes, most times, it's going to be inside a module, but sometimes it's not inside a module. I think back to my days at Subaru, we had an alarm upgrade for a glass brake sensor, and you had to plug that into the CAN network. It was optional, so yeah, it was a dealer installed accessory. So you would plug it in. It was underneath the seat. There was an open CAN bus cable connector. You would remove the 120 ohm resistor, plug in the module, and then it would power up. You have to configure it, of course, but it would power up and be up and running. So that is just one example. So you may find, if you look through a wiring diagram, something like that, you may find that there's just a dead 120 ohm resistor somewhere, and that's for maybe an optional module that might not be installed on that vehicle. So if we look at CAN, here's a simplified drawing of a CAN bus. As we said, we have CAN high and we have CAN low. We have generally your main network on a car is going to terminate pin 6 for CAN high and pin 14 for CAN low. Talk a little bit more about that in a minute. And then once again, that 120 ohm termination resistor on the end across both lines. I call that the stop sign. That's the end of your network. That's where they terminate. And what we're actually looking at when we're talking about CAN, when we get to the pattern, it might make a little more sense, I guess, but we're looking at a transmit and a receive. So the high side sends, the low side receives. And with all the crystal clocks inside the computers and the timing, they're able to time each other out so everything lines up when we're looking at it on the screen. So really the only test you can do on a CAN bus with a meter, just like a voltmeter or ohm meter, is going to be just testing the resistance of those termination resistors. If I were to hook up across pin 6 and 14, I should see about 60 ohms, give or take, a percent or two on either side. And why 60 instead of 120? Because it takes both sides, averages it out. 120 divided by 2 gives us that 60. So one nice thing about CAN is it is modular. So we can add some modules on there. They'll start communicating with each other once they're set up, of course. You want to add some more modules? Sure. Let's add some more modules. We can do that. And they'll still all communicate. They'll set themselves addresses on the network and start communicating. Now, well, it's probably been at least 10 years ago now. What it is you can have a large number of modules on a network, and it can be too many modules on that bus. So I know GM, over 10 years ago now, they came out with what they call their global A network structure. And on those vehicles, they had gotten to the point where there's too many modules. So we're going to separate out that main one CAN bus that we have. We're going to separate it onto multiple other buses in order to avoid traffic jams, data collisions. If you're sending too much data at once, it doesn't always get to where it needs to be in a timely manner. So we might have to separate them out onto individual other networks. We want to get rid of some. We can also have just one module on a network and it'll still communicate. Actually, we'll see that a little bit later. I actually have an ECM right here, and that is how we're going to show our CAN patterns a little bit later when we go live on the tool. So it still will communicate and still will transmit and receive data if it's just one on the bus there. So if we were to test CAN using a scope, those of you who are familiar with looking at CAN, you take a look at that and say, yep, that is a pretty good example pattern of CAN there. So we have two different states to our signal. There's our CAN high, there's our CAN low. CAN high, once again, pin 6, CAN low, once again, on pin 14. We have a idle state where it is not transmitting any data. That's where the bus is at rest, not transmitting anything. And then when it transmits data, that's going to be these squares here, these square waves. So these are going to be the bits and bytes, the ones and zeros. So when it goes up, It's going to go up by about a volt, volt and a quarter on the high side. And then the low side will go down. It'll drive down to about a volt, volt and a quarter. By the way, that idle state, if we're looking at both channels, we would see 2.5 volts, give or take, on both sides. And they should match on both sides as well, because it should be mirrored. So that's the basics of CAN. We'll get a little bit deeper here in a second. But another way that manufacturers have attacked this data collisions, too much going on, not being able to transmit data fast enough, some manufacturers have started using what we call FlexRay. Now, FlexRay is like CAN, but it's considerably faster. It is still a 2-wire twisted pair, just like CAN is. This one has a transmission rate of up to 10 megabits per second. So that is 10 to 20 times faster than CAN, right? So it uses a similar structure, but it is considerably faster in data transmission. And FlexRay uses a 1 volt differential. Remember how CAN had a 2 volt differential top to bottom? This is a 1 volt. And a lot of that has to do with the speed, because we have to have that rise and fall that fast to get that 10 megabits per second. Now, just like CAN, one signal circuit's going to be signal high, the other circuit's going to be signal low. And at the end of each data bus, there's a resistor. But in this case, on FlexRay, it can be anywhere from 80 to 100 ohms resistor. And another thing about FlexRay that's not mentioned on this slide, but there can be redundancy depending on how the manufacturer has it set up. So I could have 2 identical sets of FlexRay lines, wires, and if one fails, the other one can take over. So there can be redundancy built in the system. It isn't always, but there can be there. And then if we were to look at it on a scope, we'll see that it is, it's quite a bit faster. These are complete sets of data here, whereas on that CAN bus, we had maybe half the data on the screen of the whole set of data. In this case, we get almost 3 complete sets of data on the screen. So that's considerably faster because it's taking a shorter amount of time to happen. And then from here to here, about that 1 volt differential from high to low. Also, when we consider working on networks, network diagnosis, we need to also be conscious of the fact that most vehicles have a gateway module on them. And that allows us to send data between different networks, translate data between high speed, low speed, mid speed, LIN buses, whatever else is on the car, because there can be multiple types of networks. We need to use a gateway module to translate between them. So you may have heard of maybe Chrysler's secure gateway module, and that's different. So that is more of, I would think of that more like a firewall for the car. So that doesn't allow outsiders in. You have to be allowed access to get into the vehicle. So they call it a secure gateway module because it is really the gateway to the outside world, but it's not this type of gateway module we're talking about. So the way I think of a gateway module on a vehicle in this sense is it's like the router for your car. Many times it can be called out individually as a gateway module. Some vehicles just have it. It's right on the screen. Here it is, engine, transmission, ABS, gateway module. Others, like the signal acquisition module, footwell module, can often be inside the body control module as well. Give you this example. Had someone call me one day, tech call me. This was a few years ago, but still very relevant. They called me and said, "Hey, I have an engine light on this car, and I'm trying to scan and find the engine, find the codes in the engine controller, and I get no communication with my engine controller. So my scan tool must be broken. What's wrong with it? Can you help me fix it?" So I said, "Okay, let's back up a little bit. You said you can't read the engine. Can you read anything else on the car?" And they said, "Well, why would I even bother? I'm looking for an engine light, right?" But I said, "Well, just humor me. Go down the list." This is before we had the one-touch code scan on the tool. So I said, "Just go down the list and see if you can communicate with anything on the car whatsoever." So they went down the list, couldn't communicate with the engine, couldn't communicate with transmission, couldn't communicate with the brakes or the power steering. But once they get down to like the instrument cluster, airbags, radio, all of those things, he was able to communicate. Also couldn't communicate with the body control module. And he said, "Well, that's weird. I can communicate with half the car, but not the other half. Now, why is that?" So if we look at this wiring diagram right here, everything in red, the tech was not able to communicate with. That's all on the high-speed CAN. Everything in green, they were able to communicate with. That's everything on the low-speed bus. And if we look over here on the left-hand side, that is my data connector. So you'll see the first thing from that data connector, I have a low-speed line, goes right into the body control module. High-speed lines go straight into the body control module before they go out. So in this vehicle, the body control module is the gateway module. So those high-speed signals were not being able to be making it all the way to the modules. So they replaced the body control module, set it up, got it ready to roll, and magically, communication was restored with the whole vehicle. So don't just assume that the scan tool is at fault when you don't get a communication problem. I always mention, think about why the car is in your shop in the first place. Is it because it's working perfectly and there's nothing wrong with it? Probably not. It's probably because there is an issue with that car. And that issue very well could be a network problem, right? So we always have to be cognizant of the fact that these exist as well. So let's talk about using networks or testing networks. Yeah, testing networks using a scope. And you really do need a scope in order to test it. Of course, now for this class, I work for Snap-on, so I'm going to be focusing on Snap-on scan tools, but some of the techniques I'm going to show you will also be applicable to really any scope that's out there. You need at least a 2-channel scope, but there aren't that many out there that are less than 2 channels. So you should be good, I think, on testing on just about any scope out there. We do need to use that high sampling rate lab scope because of the amount, the speed of that data that's going on. We need to be able to access that. Now, if we think about CAN, those little data packets we saw before, those little bits and bytes, the ones and zeros, there's a spec built into CAN for how short one of those can last and still be considered a valid piece of data. The shortest one of those can be is 1 microsecond. So that's 1/1,000,000th of a second long. We need to be able to capture at least that small an amount of a glitch. Luckily for you, if you use a Snap-on scope, it's a 6 million samples per second on one channel. And then we divide as we add channels. So we do 2 channels, it's still 3 million samples per second, 3 times faster than we need to sample in order to catch a 1/1,000,000th of a second glitch. So we're in good shape there. When I'm going to test, let's look at a wiring diagram first. Always a good idea to figure out where my network terminates, what I'm looking at. And then oftentimes, it's easiest to just go right to the diagnostic connector. So we'll go to the pins on the DLC for whatever network we're working on as of looking at the wiring diagram. I also recommend using a breakout box of some sort because we don't want to front probe that. Because if we front probe the diagnostic connector, we probably will damage it and have a communication problem after. Probably pretty hard to back probe on that as well because they put them in not the easiest accessible spots on a car. So oftentimes pretty hard to back probe. Standard setup be a good place to start. Set voltage scale on both channels for 10 volts and then set the sweep time at 100 microseconds. And that should get you roughly where you need to be. And hopefully you get a signal on the screen. And we'll talk more about that in a minute when I go live on the tool. Here's a standardized pinout of a data link connector. Some of these other pins can be used, but standardized, we have pins 4 and 5 are going to be our ground. Pin 16 is going to be powered. Pin 1 is often used for low-speed CAN. I know on GM that they'll terminate their low-speed CAN there. It's a single wire. J1850 for variable pulse width. That's a single wire network. That's pin 2. Pulse width modulated, which is often used on Fords. That would be on pins 2 and 10. So that's a 2-wire network. Then we also have our CAN. So that's going to be pin 6 and 14. We already talked about that. K line, it's going to be on pin 7. L line, which sometimes, depending on the vehicle, can go with the K line. That's going to be on pin 15. Now we see all these other open channels there. That GM I was talking about, the global A network, those vehicles, they'll have their regular CAN, or I would say regular CAN, but their main bus on pin 6 and 14 as they need to. So engine, transmission, body control, that sort of thing. But then they'll also split out the chassis controls are on these 2 pins. And then the object detection bus is on these 2 pins, right? So it terminates 3 CAN circuits at the DLC, plus all these other circuits there as well. So we can get pretty crowded on that connector. Sometimes we have to dig under the dash and find a sub connector where they connect together as well. So here's an example breakout box. This is the one that Snap-on sells. So that's the YA11167. That's a Blue Point branded box. And there's a lot of them out there on the market. They're all pretty much set up the same way. They have a DLC on one end, 2 or 3 foot cable terminates in this box with 16 banana jacks, 1 banana jack per pin on the DLC. Other side of the box, there's another DLC, so I can hook up my scan tool. So you can be scanning the vehicle, checking for data, checking for codes, what have you, while also checking the bus with my scope on that, all using that same tool, right? So Pretty good there. Makes it a lot easier, right? We can just put our banana jacks in there, and then when we hook up, we should see something kind of like this. Now, this is just a PowerPoint animation of what we would see, and we saw a different example earlier. But we should see those data packets. So when we're thinking about CAN, we have that high range and we have the low range. This is what we're concerned about, the high, the low, and then what's taking place in the middle. So we have that 2.5 volts in the middle. That is considered the bus being at an idle state, not transmitting data. And if we think about the two words that computers know is 1 and 0, that's all they know. So it's binary, right? So computers speak binary language. So in this case, that is a 1 when it's idle. It's just transmitting a 1. When it wants to transmit data, those are our zeros. So we have 1s when it's low, 0s when it's high. So when it's transmitting, we see 0s. And then when it's not transmitting, we see 1s. As long as the idle state is at around about 2.5, and the high side doesn't go above 375, and the low side doesn't go above below 125, we're in pretty good shape. That would be considered a valid data range there. There can be other errors or issues that we might see, and we'll talk more about those in a second here. So as we said, we're only interested in the following thresholds: the high side, low side, and that 2.5 volts in the middle. So this is an example of a good pattern, what you would see. So I have my high side, my low side are between the 375 and the 1.25. Everything is perfectly mirrored. They're the same voltage on both sides, which is what we want to see as well. If one is higher than the other, one's lower than the other, we could have a problem there. Well, crisp 2.5 voltage line with no line noise. We don't want to see any noise in there. Vertical and horizontal corners need to be crisp and clean with horizontal peaks at the dominant top and bottom. Here's another example. Let's say we had some noise in there, a lot of RF noise or EMI. That would cause a problem on the bus. The packet still might look okay, but then I would have a lot of noise. If we get noise introduced into a module, the network will still be stable, but whatever controller is causing that issue, or whatever controller is transmitting this data with the noise, gets dropped off, gets kicked off the network, and then we will get intermittent malfunctions and U codes as well. So if we think about codes related to CAN, they're all going to start with a U, right? And U stands for UART, which is a computer type language term there. And that is that's what all the U codes will stand for. U codes aren't all that descriptive either, which makes it a bit of a challenge using those codes to diagnose. Here's an example of weak packets. So I have some good packets over here. I have some good packets over here. And then I have a bunch of weak, not nearly as high, not nearly as low, weak data packets. That generally indicates controller internal shorts to ground. When we have an error like this, it's going to drop off the network, and then people are going to stop asking for information, or the modules are going to stop asking for information from it. So that means request abort, causes intermittent problems, and erroneous U codes again. You're going to see a running theme here anytime we have any of these problems. So we look at a high side, we're talking about problems. Normal is here, 375. Shorted to voltage might be high up here, 5 volts, 12 volts. Shorted to ground would be down here, down around 0. So we could have any of these issues on the network. That's the high side. Same with the low side. We could have a short to ground, normal, or short to power. So that's what we're going to be looking for. And I'll be able to give you a couple live examples of this in a couple minutes when we go live on the tool. Both sides could also be short to ground. Both sides can be normal, and then both sides could be shorted high. And then I could have one normal and shorted to ground, both normal, or one shorted to power and normal there. We can see how we would have the higher and the lower sides on those square waves. Here's just another example, different drawing of what that would look like, right? So not mirrored indicates we have these, a couple of these driving closer to ground. The high side's still good, but the low side's coming towards ground. So that indicates internal shorts to power or ground, depending on which way it goes. If it goes down to ground, it's a short to ground. If it goes to power, it's a short to power. Once again, causes intermittent malfunctions, U codes. And then what do we have going on here? Holy cow, we got a lot going on here. High, low, up, down, all around, all sorts of things going on. That's something wrong with the controller for sure. And then when that happens, packet drops off, U codes. So if I have a fault, how do we A, figure out where the fault is, and B, how do we fix that fault? Oftentimes it's going to be replacing a module, but when a controller is out of range, those signals are either higher or lower than expected. So they go outside of that known good range there. At that point, the system drops its packets and it calls for an error. It says, hey, this module is not doing what it's supposed to be doing. It is talking a very foreign language, or it's not communicating very well at all. If I have a scope pattern where I have too high a voltage, like it's shorted to 5 volts or something, start disrupting power source of the controller until it restores its voltage range. So I could go one at a time to narrow down the controllers. If it's much lower than expected, you can start removing controllers once again, find the controller. If I go to my engine, unplug the network. Did my signal get better? No, plug it back in. Go to the transmission, unplug it. Did it get better? No, okay, plug it back in. Go to the airbag, unplug it. Hey, pattern got better. There's your problem, right? It's just the process of elimination in order to be able to find where the problem is. Now, bus faults. Bus, when we refer to CAN bus, I know it kind of gets used and thrown out there, meaning a lot of things, but when we're actually talking about the bus, that's the physical wiring connectors and such. So bus faults would be usually caused by external damage to the circuit itself. So I would maybe see a broken wiring harness or some sort of an issue in the wiring harness. Maybe the vehicle was in a collision and I have some sort of problem there. These types of faults need physical inspection and testing on the circuit's integrity itself. I want to make sure that the wires are physically okay and they're not frayed or chipped or broken. Now, we could have short to ground on one side and not the other side, and it would still transmit. It's going to switch to a lower frequency and it's still going to transmit, but we could still get error messages. If my low side goes and not my high side, remains stable, switches to a lower frequency, but once again, gets dropped off the network eventually. If both sides are short, usually physical damage is the problem. So all communication will be lost past that point on the network. And like I said, most likely physical damage. All right, so we got the theory out of the way. Now let's look at like a real life situation. All right, so let me pull up my tool here. So first off, let's talk about wiring diagrams. Let's go and look at a wiring diagram. So I'm going to go in here. Let's say 16 BMW 328. And let's look at the networks. I'm going to pop into shop key here real quick. Pick an engine. Okay, if I go, if you have shop key, you have the quick links right on the front page. Going to give you a link directly to all the wiring diagrams on the vehicle. This just makes it easier if I want to see a whole network overview. I can go to my computer data lines. Your mileage may vary depending on where you are or what you're using for information systems. So we see it's 5 pages long. I'm going to go through here and try and find the diagnostic connector. So we got a little ways. It might have been on that first page, but I don't think so. 3, page 3. There we go, page 4. So here's my diagnostic connector on the top. Go in here a little bit closer. All right, so we know 16's power. We know 4 and 5 are ground. So we have an orange wire, we have this gray wire, we have this yellow wire, black and red. We got a lot of networks going on here. Let's find out where they go. We know 6 and 14 are going to be CAN, right? So got all that. Let's get rid of the noise. All right, so where do these go? Let's zoom up. So I got these 2 pins. That looks like 15 and 7. They seem to pin out in the harness there. Let's go to the right. See where that goes. It's going to come across, and that is going to be a terminating resistor. So in that case, that is an open circuit, and that is going to be that 120 ohm resistor plugged in across those 2 lines, right? So that would be an open line, and that is our terminating resistor there. Now let's see, did I have any down below? I don't think I did. No, we're good there. Okay. Go back left, gonna keep our highlights across. Oh, let's see, one goes down to, let's see, what pin was that? That was pin 9. Pin 9 goes directly to Internet's slow tonight. What is this thing? That's the DME. So that goes directly to the computer. So that goes directly to the engine computer there. Where do the other lines go? They're going to go to other modules, right? So I'm guessing on the left-hand side, there's probably a gateway module in here somewhere. Let's see, go across that page. And go across that page, back to the beginning. And then we see that those all terminate at the front something. Let's scroll down and find out what that front something is. My vision is not as good as it used to be. All right, let's see. A little more. There we go. Front electronic module, which is the right end of the dash. So that is what operates as the gateway module on this vehicle. And if we look at all the data lines here, I got PTEN, which is powertrain CAN, wake up signal, K line, which stands for keyword, by the way. So K line stands for keyword. I saw a question pop up there on that. Let's see, PTEN, powertrain CAN, bus signals, AC LIN bus signal, FlexRay bus. So this has a FlexRay bus on this car. BMWs do use that quite a bit. So that's going to be the pink and green lines. That's going to be FlexRay. More data lines here. The data lines up here go back to the DLC. We got KCAN, which is going to be a different speed of CAN, right? And then power supply. So this module is used as my gateway module. So that also gives us kind of a testing point there too. If we really need to, we can find this and we can pull the connector and we'd be able to check communication on multiple circuits with that. You probably want to start at the DLC, but if you can't do that, now let's say, for example, I couldn't talk to the head unit, the base plate, any of these. Well, maybe I have a break in the line right here at whatever these splices are inside the line, right? So it's always good to read through the wiring diagram and get your bearings as to what controller is hooked up to what and what is where on the network, and then we can go to approaching actually testing it. All right, so that's just one example of a wiring diagram. Now, if you have a snap-on tool with a scope in it, so that'd be a Zeus, a Verus, Modus, a Triton, or a Vantage, or a Verdict. Any of those, we have built-in guided component tests. So this is the easiest way to go in and look at anything on a car, really, any component that you can test. But also included with this is going to be training and classes. So with this, if I forget everything that I said today, I could still go into how to. And there are 65 categories of class. There's a LIN bus class. There's NOx class, ignition classes in here. But the one I want to focus on is going to be CAN bus. There's a 20-minute CAN bus class inside the tool. Comes with it. We have basics and fundamentals of CAN. It's going to tell you how it works. 500,000 bits per second, which is 500 kilobits per second. CAN high, CAN low. It's going to tell you a lot of the things I just told you. Bus arbitration. This tells you who gets to talk first on the network. CAN voltages. It's going to tell us our CAN high and our CAN low voltages, what we want to see. They should be mirror images. Talk about dominant and recessive. Error handling. How does it handle with an error on the network? Signal quality, right? We want to see how the signal needs to be of the highest importance on the CAN bus network, and we talk about that. But this one's pretty key right here, waveforms. So waveforms will show you on the screen. Here's a good one. Here's one where the low side is open. Here's one where the high side is open. Here's one where the low side is shorted to positive voltage. See how the low side's above the high side, so that's a higher voltage. Depending on where the short circuit is, they could both be shorted high, depending on where it's at. This one shows CAN high, shorted high. Once again, depending on where they're shorted, could be high. This one shows low signal wire shorted to ground. Depending on where the short is, we could have a different image where we go into that higher speed transmission rate and we get the larger data packets. This one's high signal shorted to ground, and so on and so forth. And here is both signals shorted together. Right? So if they're shorted together, they're going to match each other evenly because they're transmitting the same data at the same time. But they could also have a flat line. And then here is my known good again. It's going to tell me where to hook up to pin 6 and 14. In this class, I could hit view meter It's going to set my voltage range where it needs to be, and it sets my time base where it needs to be. And I have a CAN pattern, just like that. All right, so there's my CAN pattern on the screen. Now we'll analyze this in a little bit. I'm going to walk you through a couple other ways we get to that. So that's just through the class. If I wanted to look at a vehicle specific, so let's go with our, let's go to BMW again, 2012, 328i. All right, let's look at that. So once we load a vehicle, this is all VIN specific information, by the way. There's over 5 million tests, goes back to 1981. In the engine system is going to be where I can find my CAN bus. I can also find if there's FlexRay or any other types of buses, oftentimes they'll be in here as well. Crank sensor, cam sensor, but I want to look at the CAN bus. You can go to component information to learn all about it, or I can do a signature test. Signature test is going to show me what that CAN bus is supposed to look like. It's going to tell me where to hook up. So if I have a snap-on tool, it's color coded, right? So if yellow, black, and green, yellow is going to be channel 1, green is going to be channel 2, and then black goes to a known good ground. We'll see this pattern right here, and that pattern looks a little bit different, right? So in this pattern, we have this extra little blip at the end. Actually, let me switch over real quick. Let me switch over to my BMW here. Actually, turn that off a little earlier. So I want to talk about this too, because that can throw you off. If you're not sure what that is that you're looking at, that might throw you off. So let's talk about that real quick too. So let me hook up to my beamer. All right. So if I hit view meter, it's going to pull up my beamer, and there's my CAN bus pattern on the beamer. All right, looking at 500 microseconds here, so we're not as close as we were before. You can see the data packets look fairly similar to how they were before in this part, but then we have this high spike at the end. And this does throw some techs off when we have this high spike. Well, I thought I wasn't supposed to go that high or that low. In this instance, some manufacturers, depending on how they have their network set up, some manufacturers may have this larger bit at the end. They call that an ACK bit or an acknowledgement bit. I like to think of that as the period at the end of the sentence. So the module is going to transmit its data, and that's the end of the data. And then it's going to transmit more data. That's the end of the data. It gives this acknowledgement that, yes, this is the end. And then the controllers that receive it say, yes, I received it. Right. So we're going to have this acknowledgement bit on some vehicles. In this case, on this BMW. Some vehicles have it, some vehicles don't. So just don't be surprised if you do see it. Don't be surprised if you don't see it. Right? It depends on the vehicle and how it's set up. So it tells us exactly where to hook up. It tells us where to hook up on the vehicle, and gives us a known good pattern, and it sets it all up for us. That is really the easiest way to go about testing CAN on a vehicle. Now, maybe you don't want to use that. Maybe you don't have a snap-on tool. That's fine. We can just use a straight scope. So if I go into scope multimeter, and I'm going to pull up my lab scope, I'm just going to pull up my regular 4-channel lab scope. Now I have my BMW here, but I want to go on to my Subaru because I can do a little bit more with this actual control module. So let's do that. All right, so there we go. That should be good there. All right, so this is actual data coming out of a 2008 Subaru STI PCM here. And this is going to give us our signal. So this will be considered a normal signal. You'll notice on this vehicle, we do not have the ACK bit on here. So it just sends out data. There's no ACK bit at the end. I have it set up to 10 volts on both channels, 200 microseconds on both channels. I like to give it 10 volts. You could do 5 volts because it doesn't go that high. But if it's set it to 10 volts, at least it gives us that little bit of headroom. So if it is shorted to 5 volts, we'd be able to see that. And then down here at the bottom, if it was shorted to ground, we'd be able to see that as well. Just gives us that little extra room. If I wanted to, you could set them both to 5 volts. That's fine. You know, whatever you like in order to be able to see it on the screen best for you, right? That's the goal when using a scope, is just put it on the screen so I can see it and I can analyze it and what looks best to me. So in my case, I think if I had a 5 volt spike, it'd go off the edge of the screen there. So I like having that head. So we'll go back. Call me picky, that's what I like. All right, so we'll put that. I like them kind of in the middle too. Makes it a little easier. All right, so there is my known good pattern as we've seen already, right? So I'm going to stop this and let's do some measurements. Pull my measurements, pull up my cursors. So we know we have an idle state. And we know we have a state where we're transmitting data right about there. So let's use our cursor measurements. On my idle state on both channels or both lines, I am seeing 2.46 and 2.45. That is very, very close to 2.5 volts. So that's close enough for testing purposes in this environment. If you're on a real live car, it's probably going to be really pretty close to 2.5, but that's really close. And then when it transmits, goes up by about a volt, volt and a quarter, goes down by about a volt, volt and a quarter. And you'll notice it's not exactly the straightest line in the world. Once again, testing conditions is the best we can get. So it looks like the high side went up, volt and a quarter. Low side went down, 1.31. That's pretty close, 0.06 difference. So that's within the realm of possibility there. You do see, I see a little bit of difference on each one, right? So we have those going there. So that is a good pattern. Let's take a look. Let me turn off my cursors here so we can get a better look here. Let's take a look at some issues. Let's cause some issues here. This didn't quite happen the last time I did it. I don't know why, but okay, so I just removed the ground. And now you can see the difference in the pattern, right? We're going up and down. I just removed the ground. So if you don't ground your scope properly when you're testing this, you could get a look like this. I've also seen this happen when on a vehicle with a ground problem would give us a look like this because we don't actually have a good connection to ground. So if I actually went out a little bit further, maybe to like a millisecond, you can see it's going kind of crazy there, right? So that is what happens when we remove the ground. You go back in here. Let's re-add the ground. Okay. Now let's short to ground. So I'm going to take my green channel and I'm going to short it to ground. So that's the kind of look we would get shorted to ground, right? So now we see the high side. Actually, let me stop this so we can analyze. Get my hand back on there. It's very good. There we go. So let's stop it and analyze this. Okay, so the low side shorted to ground. Let's measure. Good enough. Okay, so we'll go to cursors. Turn on. Okay, so we have a data packet and we have a low side. So on my low side, in this case, or on my idle state where I'm not transmitting, pretty much 0 volts. 0.08 on my high side, negative 0.01 on my low side. So yeah, pretty darn close to pretty much 0 volts, shorted to ground. When it transmits, we're getting 3.49 volts, which is about where we were, about 3.5 volts on the high side. So the high side still transmits, but the bottom gets pulled down to ground in this case. All right, so that's a problem. Actually, my high side's actually a little loose too. So, there we go. All right, so we got that. So that is low side shorted to ground. Let's see if we get anything different if I short the high side to ground. So let's do the same thing. Short to ground. Short the high side to ground, I lose everything. Now, why is that? Because one's going in, one's going out. So in this case, that data is not making it through and back around because I'm shorting it to ground before it gets there. I remove the ground, I transmit data again. So low side in this case, shorted to ground, I get this. High side shorted to ground, I get this, flat 0 volts. So depending on where it is in the network, that'll give you that indication as to where the problem might be. Now, what if I short the two together? Short the two together, it doesn't get very happy, and it's about 2.5. Well, I get a little bit of transmission there, about 2.5 volts. All right. Now let's short to power. One more thing before we got a few more minutes before we can get to questions. So let's short to power. So I'm going to short the high side to 5 volts first. See what happens. All right. So there's my high side shorted to 5 volts. You'll see the low side kind of acts like the high side did when we shorted the low side to ground, right? So it's a very similar look. It's just going the other direction. So the low side still has its low, about 1.5 volts or so. And then the high side is at 5 volts. All right, so we're doing 5 volts. Now let's short the low side to 5 volts. Short the low side to 5 volts. We get a little bit of something going on, but not a whole lot of something because once again, we're sucking all the juice out and not a lot going on there. So it's shorted to ground right there. So, I'm sorry, that's short to power. Sorry, short to power. Short to 5 volt power. So we got a lot, it's not liking it. It's not transmitting. Remove the 5 volt power problem, I'm back. How about an intermittent? All right, we got intermittents. How about an intermittent short to ground? Sometimes you can't even catch it so fast. There we go. All right, intermittent short to ground, can catch it there. All right, so those are mainly the different states you're going to find when it comes to CAN. Short to ground, short to power, short together. I can't simulate noise. I don't have an EMF generator right here that I can simulate any noise on. So you just have to know that it would look really, really fuzzy. You'd see a lot of look like maybe static, a lot of ups and downs, peaks and valleys going on there. So that is basically what we need to talk about today as far as diagnosing some network issues. So it looks like we got some questions coming through here, and let's address those. How about? So let's see. First off, we got Kenneth. So Kenneth asks, is the Vantage Pro fast enough for testing bus networks? Yes, it is. So the Vantage Pro is as fast as any of our other scopes that we have. So 6 million samples per second on one channel, and then we divide by however many channels we're using. So if you're using 2 channels on that Vantage Pro, it's going to be 3 million samples on both sides. So yes, definitely fast enough. Jose says, never knew there was training on the tool in the Veris. Nice. Yeah. So that's actually been in there for a little while, but the problem was we hid it under like 3 menus. So a couple years ago, we added in a software update. We actually brought it more to the top of the menu there. So definitely. Let's see. Ben says, did I say the classes were in Shopkey? So the classes themselves are not in Shopkey. So those training and classes that we have inside the tool are not inside Shopkey. They are inside the guided component test portion of the tool with that. All right. Clint, thank you very much. Trying to do just this for 50 plus years, man. More power to you. Definitely appreciate you spending your time in there with that. All right. So let's see, is this, Luis says, the circuit always running on the 5-volt circuit? Well, we got 2.5 volts on both sides. So it's really that differential. It doesn't quite get all the way to that 5 volts. And that's a good thing, right? So if it's shorted to 5 volts, that's an anomaly. That's too high. That's up here, right? And then we have the low side down there, short to ground. So you're looking at a 2.5 volt range. So it's a little less than 5 volts, whatever. So I hope that answered your question. That was a little kind of confusing the way I even said that. Thank you, James, for chiming in. Hey, Enrique, thank you for joining us from Sun and Snap-on in Mexico. I think you've been to a few of my classes before. Definitely thank you. Thomas asks, and I'll get to some of them now, and I'll get to some of them after too, as I do have a little bit more information I want to mention before. Do all CAN circuits behave this way when shorted to ground or power, or is it just a situation that I show? Thomas asked that. So as I mentioned during the course, it depends on where in the circuit it's shorted. But by and large, those are going to be the main types of anomalies you're going to see in there. Sometimes it's not quite that full short all the way to ground either. So I might just have a little bit dip. Maybe I lose a 0.5 volt or 3/4 of a volt or a whole volt. That might give you a little bit different. I can't simulate that here, unfortunately, but definitely something. Okay, so got some more questions in here. We'll get to those. Keep adding if you do have questions in there. Definitely keep adding those. I'll address those in a minute. I just want to talk about a few other things, not necessarily CAN bus related, but related to training, right? We all like getting as much training as we possibly can. And I will tell you that we try as Snap-on, we try to give you as much training as we can possibly can. Every 4 days a week. 4 days a week, we offer free online training through Zoom. So on Tuesdays, I offer 2 classes. It's the same class, it's just 2 different time slots. So 6 and 9 Eastern time, whatever your time zone in translates to that. If you go to snapon.com/OT, you can register, join us on Zoom just like we are here right now. As I said, every single Tuesday. Unless I'm on vacation, which happened once. But other than that, every Tuesday we are there on Zoom. I also will simulcast or simultaneously stream session 1 to YouTube on the Snap-on Diagnostics channel. So if you go to youtube.com/Snap-on Diagnostics, you can subscribe there, ring that bell, make sure that you get notification when we start streaming. And then session 2 streams live on Facebook. So on my Facebook page. So Jason Gabrenas, Snap-on Trainer. You want to look that up on Facebook and give me a follow there. Just hit 1,000 followers over the weekend, so I'm pretty happy about that. Thank you, anyone on here who does currently follow. That's it's much appreciated. And try to give you as much access, as many different places as we can get this information as possible. Now, the other nice thing is not only do we do these classes live, but we also archive the live class. The first time we do a class, because I'll also tell you we do about 5 topics. We'll do them for 5 weeks in a row, and then we'll repeat those same 5 topics again. So that gives you 4 opportunities to watch it live and ask questions. After that, we'll create 5 more classes, do them for 5 weeks, repeat. So these are the past classes that we have archived on YouTube as of right now. So that's once again, youtube.com/Snap-on Diagnostics. So that is, intro to ADAS component testing, data bus testing and diagnosis. That is our most popular one. And that's actually why we decided to do this class tonight, because it seemed like it's a pretty hot topic out there. Thermal imager diagnostics, module setup, coding, programming, flashing. What's the difference? Adjusted ignition testing, right? So multiple different topics there. You can always go back. We have a playlist for live training sessions that are there. And then the other 3 days of the week, remember how I said we do 4 days a week? My buddy Al, who's my counterpart, we're a department of 2. So he does tool training. So Mondays he does Apollo, Wednesdays nights he does Zeus, and Thursday night he does Triton. So this is everything from let's set up your Wi-Fi through let's set up your free Snap-on cloud account so you can back up images and you can send reports to customers and things like that. All the way through code to completion, going through a case study scenario on intelligent diagnostics and shows you how it works and how it helps you become more efficient as a tech. So as I said, Mondays Apollo, that's about an hour long. And then Wednesdays and Thursdays on Zeus and Triton, those are about 2 hours long. So after that first hour where he covers the scan tool material, take a little break, and then he comes back and covers the scope, the graphing meter, the digital meter, the guided component test meter, all of that information as well in those 2 classes. So those are pretty much closer to 2 hour long. Same time as my classes, so 5 and 8 Central, 6 and 9 Eastern. Go to that snapon.com/OT. Pick on your platform there, and you'll be able to register for any of Al's classes as well. Al is definitely a veteran of Snap-on Diagnostics. He came over with the brick, so 30 plus years of Snap-on Diagnostic experience. So definitely worth your time and effort for that. All right, so that's my advertisement for the night. Okay, so first one we got here. So James says, so CAN low is the send, high is the return. It's actually opposite. So high sends, low returns, but close enough. Can you tell about which module is sending the individual data packets, or do the waveforms change when you unplug one module? So the thing about CAN is it's set up like a mesh. So everybody's talking at once. So everybody's transmitting at the same time. They do go in an order set up by one of the master controllers in there. They do go in an order, but everybody's transmitting their data at the same time. They might just have to wait to transmit. When you unplug one module, it's going to look pretty much the same. There is specialized software out there that you could find that's able to decode what's actually in those data packets. And you might be able to figure out, if you could figure out the module identifier, what module it was. But mainly we just want to see, does it look good? If it doesn't look good, let's unplug one. Did it get better? There's my problem. If it didn't get better, that's not my problem. Right. So it's just a process of elimination in that case. Thanks, James. Difference between CAN and CAN FD. The big difference between CAN and CAN FD, the way I understand it anyways, is that CAN FD is that faster version of CAN. So that is, it goes from the regular CAN was a max of 500 kilobits per second. CAN FD is up to that one megabit per second. So 1,000 kilobits per second. So it's faster CAN is basically what it is. Let's see. Corrupted module, would the signal look the same with a spike in the pattern? So depending on how it's corrupted. So if I had a short to ground, I'd see intermittent shorts to ground. The thing about CAN is, as I said, they all talk at once. So if I lose one, everybody else can still talk and transmit more than likely, unless I have an actual physical problem with the bus. So I might see bad packets, good packets, bad packets, good packets, just depending on where in that line that controller is transmitting their data, right? So having that, narrowing it down where it's going. Yeah, so you may see a difference in the pattern, but you won't necessarily be able to know what module it is until you go and unplug it. All right. So, okay, so Brandon says, what about when you pull codes with a Snap-on scanner, codes display, but at the top says network unavailable? So that is a different kind of network. So we're in that case on a scan tool, when we're pulling codes, that is your Wi-Fi. So that just means you're not connected to your Wi-Fi, and you want to definitely get hooked up to your Wi-Fi so you can get a little bit more information on that one, Brandon. So let's see. Vertical resolution on Snap-on scopes. I don't have that one off the top of my head, but I will. How high can we go? I think that might be what you're trying to say. What's the max scale? So 400 volts max scale, if that's what we're looking for there. 400 volts max scale, and that's the max that'll do on voltage. If we go into ignition, yeah. On ignition, we can go up to 50,000 volts without an attenuator, by the way. Don't need an attenuator for that if we're doing ignition. So hope that answered your question. Other than that, like the techie specs down to the chips and stuff like that, I don't have that off the top of my head. I'm sorry about that. All right, let's see. Okay, so why do the red and blue test leads for the Veris not include a ground lead? I know the green and yellow leads do. So the yellow lead has 2 straight ends, right? So that is your actual ground for the scope. On the other end, you're going to have a right angle with a flat top and a right angle with an extra little thing coming off the top. That is for stacking the ground. So the one that you want to hook up on the ground lead is going to be the black one without the extra thing on the top. So it's just a flat top on the 90 degree. That is the actual ground cable. So that will ground it. The red and the blue, they're not shielded as much as the green and the yellow. So the green and the yellow have an actual shield that can be grounded as well, which allows us, in case we have some noise out there, to be able to reject that noise and get rid of that noise. So that's why you'll see that on the green and the yellow, and then the red and the blue, those are just for your extra channels there. So you do need to ground it, but you still could use that channel 3 and 4, and you don't need to ground those. Okay, Bill asks, is there commonly a splice pack where nodes for different modules can be removed from the bus in order to facilitate isolating shorts? Yes, but it depends on the manufacturer. So let me see if I can find one. Let me remember one I think it was a 15 GMC Sierra I worked on that had that. So depending on the vehicle, they may be configured in what they call a star configuration, which is what you're describing here. So it'd be a splice pack somewhere under the dash, could be multiples underneath the dash, and that's where all the modules have one wire that goes into a central location underneath the dash. So let me pull up my system wiring diagrams and my computer data lines for that. So let's see how this looks. So looks promising, looks promising. There we go. There we go. I had it right there. There we go. Splice pack. So on this vehicle, I think there's probably more than one, but this is the first one I saw, so I stopped on it. So this is your splice pack, and this is a centralized location where all the modules will have a line going in, and then that allows communication, but there's a shorting bar that goes in between all those. If you remove that shorting bar, you can then test through that connector. So when GM tells you to test it, you can use a jumper wire. So usually one of the pins is going to go back to the DLC, and then maybe the next one's the engine, next one's transmission, next one's body. So I can just use a jumper wire to see if I can get communication that way through there. Also, there is, if you can find one, it has been discontinued, but there was a tool we used to sell called an EEFF 500 data bus fault finder that would allow you to automatically check for shorts and opens, short to power and ground on the lines, and then be able to individually take those out of the network as well. So depends on the manufacturer. I'll tell you, on on Subaru, because that's the one I know the most about, right? So Subaru, half the cars, the ones that are made in the States in Indiana, don't have them. The ones that are made over in Japan, those do have them. So it just depends on the manufacturer and how they decided to set it up. So yeah, definitely, if you can, if you can get to it, makes it easier. All right, thanks, Bill. Harley, thank you for the love, right? Excellent class, loved it, very informative. Love being able to help you use your Veris to its fullest potential. There is so much stuff inside our tools. And I always tell people, I could come to your shop for 30 days and you still probably wouldn't get to half of what that tool is capable of doing. So there's a lot of stuff in there, and definitely looking forward to seeing you in class. So thank you very much. Definitely appreciate your time. Let's see, how to get hands-on CAN bus training in the future. Well, for me, I don't really know because when I can go out and do hands-on, depending on where you are there, Zishan. I hope I'm not butchering your name, by the way, but it looks like Zishan, Aziz. Depending on where you are, I'm not sure where you are in the world. Are you in the States? You're in Canada, in Mexico? Not really sure, or it could be in Europe. I'm not sure. Depends. You may have a local diagnostic rep in your area that might be able to help you out with that as well, hands-on training there. The biggest thing I always say is just, if you have a Snap-on scan tool, go in with the guided component tests and test CAN on a car. That way you can see what good looks like. Let's see. Thank you. Also, Angel says, have a U0121 code. Good luck on a Jeep. And I'm going to try and test and apply to lessons. Perfect. That's great. I always love when you can go to a class and then use it right away so you don't forget what happened in the class. So that's wonderful. All right, Virgil, thank you very much for showing up. Let's see. Vantage. Is there a collision counter on the Vantage? No, I wouldn't say so. Not really sure what you're referring to there, Mike, as a collision counter, but the Vantage is a scope and guided component tester only. I would guess collision counter would probably be in like in scanner, but that's not a scanner, so that wouldn't have that. I'm guessing that's what it was. Could a shorted bus cause damage to a scan tool or a scan module? It depends. I'm going to go with it depends. Because I think we've probably all heard the stories before. The Volkswagen, you put an aftermarket radio in. These are older Volkswagens, not newer ones. But if you put a radio in the wrong Volkswagen, it would send 12 volts down a line. It's supposed to not see 12 volts. And yeah, you could fry a scan tool that way. I think by now, at least our scan tools have protection in there where it wouldn't happen. But you never know, right? So if it's shorted to enough power and it went down the line, it's not supposed to see that much power. That could definitely be a thing. So thank you very much for your question there, Cody. Howard, thank you for attending very much. One of the most common causes of shorts to ground or power? I don't really know. It kind of depends on the vehicle, I would say. You'd have to depend on what the most common things are. But I would say the most common failures you're probably going to see, at least in my experience, are going to be failures internally shorted inside the module. Could be a flooded car, right? If the car was flooded, that'd cause all sorts of shorts inside once the module. Actually had a BMW with that kind of problem. It was an older one. It had the round connector under the hood still, but it had the OBD2 under the dash. Had no communication with the ECM. Traced it back to had a connector where they were all spliced together under the footwell, and the car had gotten flooded, so it was all green and crusty. So that was the problem right there. So that was it's a one-off situation. So definitely, well, that'll cause a bus problem. Usually it's a module, some sort of internal power of the module. Let's see. Jose asks, is there a training class for the Veris Edge? But I just follow the Zeus class to get me close. Yeah, I mean, with the Zeus class, it's focused on intelligent diagnostics, but a lot of the buttons are the same. So that wouldn't be terrible. Also, if you go to our website, so diagnostics.snapon.com, if you go there, you can access free web-based video training for the Veris Edge is up there. I think there's like 12 or 13 different modules, goes everywhere from basic setup through scope functions, guided component test functions there. All right, thank you very much. Let's see, Sadeki Sacker, I believe it is. Thank you very much. James Jacobson, thank you very much. Let's see, CAN system looks similar to SCSI. I bet you it does, because it's, or SCSI, yeah, that's right, SCSI. So yeah, I was around back then too, back in the 80s and 90s working on computers, right? So I mean, it's data transfer to network, right? So SCSI would be much slower than CAN, but yeah, it's just ons and off, ones and zeros, man. It's all the same thing. So it's probably at a very much higher sample rate on CAN than it would be on SCSI, right? Bill, thank you very much. Let's see. Anonymous attendee asks, so each of the data packets can contain different data for their corresponding controller? Yes. So let's say the engine controller is sending out engine speed, and then it sends out the ABS controller will send out wheel speed, and the engine controller sends out something else. So it's going to send out packets of data, bunches of data at the same time, just kind of in bursts as to where it goes. And then whatever module needs that data, say the transmission controller needs input from the engine controller as to what the RPM is, the load, the throttle position, it would take what it needs and then it just uses it that way. Hopefully that would answer your question there. David, we need a class on Ethernet for Mercedes and Volvo. So if you go on YouTube, what we have right now anyways, we may get a little bit more in depth, but what we have right now, if you go on YouTube and you go to the live stream archive, data bus testing and analysis part 2, I go through Ethernet and how it works. And it is a totally different animal, unlike any other. So you might want to check that one out, Dave. And I know you come to my classes during the week too sometimes, so definitely appreciate that. Okay, so James is clarifying his question from before, 8-bit or 12-bit vertical resolutions. That is one of the ones I don't know off the top of my head. We would have to get back to you on that. Let's see, breakout at DLC, best or easiest way to scope a CAN signal? Absolutely, Bill. As long as the problem can be addressed that way. Sometimes some of the networks where we have a problem is only internal in the vehicle too, so we wouldn't be able to access it there. But most likely, especially if it's a communication problem with the scan tool, that would be the best place to go. Let's see, Tim Richardson asked, do you test with key on engine off or key on engine running? Could be either way. Those patterns that I captured, any of the patterns are just key on engine off. If you don't have any data transmitting, you might want to turn the engine on, then you might get a little bit more data going on there. Let's see. So Robert says, is splice pack in CAN or is it in GM class 2? It is mainly in class 2, but I have seen them on vehicles with CAN as well. Like, I always go back to Subaru, but my car, I have a 2011 Forester that has a big old splice pack right above the fuse box. And the splices look like fuses. So I just remember that from training. They said, hey, it looks like a fuse box, but don't you dare pull those things or you're going to lose communication in the vehicle. So yeah, it depends on the vehicle. Most commonly, yeah, the GM is going to have it, but lots of manufacturers do use splice packs on their vehicle. Tyler, when we're done. When we're done, absolutely. Let's see. Zishan. Hey, I got it right. Excellent. Excellent. Now I have a name that is kind of hard to pronounce too. My last name, Gabrenas. It's usually pretty hard to pronounce, so I can definitely appreciate that. So Saskatoon, Saskatchewan, I bet you have talked to your Snap-on representative. I bet you have a Snap-on diagnostic sales developers, what they call them up there, and our Canadian DSDs are all top notch. So put you in contact with them and they should be able to help you. Let's see. Joseph says, class is helpful, but I'm getting started with scope and wiring diagrams. What would I suggest on a class I should start with? If you have a Snap-on tool, definitely go into those guided component tests and then the training and classes right there, right from that front screen. Like I said, 65 different categories, and you can just go through there. You don't have to hook up to a car. You can just go in there and access it at any time. Otherwise, like I said, we do class every week, and usually I try to do something on scope most times. Sometimes we do scanner, but a lot of times it's scope. I do have some basic scope classes up there on YouTube as well. You can check out. There's plenty of information out there. So I would recommend YouTube videos. Have your tool in front of you and function through it. The best I can tell you. Edward, I agree. So he says, many manufacturers' testing routines call for using their diag tool network test. I've seen this and used it with my Edge, but not all vehicles seem to be covered. So it's so important, just a simple test ID what modules are actually online. That should be mandatory. And I agree, it should be mandatory. I would imagine in our case, we try to get in as many manufacturers as have it. I would bet that not every manufacturer even supports it yet. And I think it definitely should be mandatory. I definitely would agree. Thanks, Pete, for attending. Thanks for your comment. Eric, thanks very much. Glad you enjoyed the class. Let's see. Jose asks, is there a description of the various PIDs you find when you scan the data? On some vehicles, if you have troubleshooter available, if you have a snap-on scan tool, once again, if you have troubleshooter available in the engine module, there is fast track data scan. If you find that, that gives a description of the PIDs and what the value should be. Also, sometimes inside Shopkey, there should be some of that information in there as well. John, hello from New Jersey. I'm in Connecticut, so I'm not that far from you. And New Jersey actually is a very, very beautiful place. I like it. Let's see. Mike, would I recommend one of the OBD2 breakout boxes with the lights over one without? So that depends on what you're trying to use it for. So the ones with the lights are nice. I know we make one, but over in the UK, I don't even know if we have it available in the States. But when you plug it in and you have lights with signals right on there, that gives you a quick visual. Otherwise, if you just simply need to test, you can use the one without. Either or, I guess it's just a matter of personal preference. Okay, Kelvin wants me to clarify the website. So it's diagnostics. So diagnostics with an S at the end, .snapon, all one word, no dash, .com. And then that'll bring you to our diagnostics website. Go up on, I think it's not, yeah, it's still on the top, training and classes or training, and then it'll bring you to the training link. Let's see, looking forward to the email presentation within the next few days. Yes, we are recording this. We are going to have it as an on-demand webinar after the fact. And definitely, that's no problem, no problem. Glad you enjoyed it. Yeah, Robert, I definitely wish they all had a splice pack too. That'd make life a lot easier. Bob, thanks for coming. Thank you, Enrique. Glad you could join us. Let's see. One module is offline. We'll be able to see that on a lab scope. Probably not. Probably not. There's a square flat line of the module in the middle of the circuit and continue. So it's going to be usually the same spacing in between modules transmitting. So I don't think you'd be able to notice that on there. Probably the best way to do it is try to scan it, get codes data, and see if it communicates or not. Thank you, Rodney. Thank you, Jack. And thank you, Galaxy A10E. Glad you could join us. Kenneth, what is the difference between Mitchell 1 and Shopkey? I'm going to show you on the screen right now. What's the difference? This right here. Just the logo on the top. We own Mitchell 1. Snap-on owns Mitchell 1 and Shopkey. It just depends on who sells it. So Mitchell sells Mitchell. Your Snap-on rep and your franchisee sell Shopkey. Just two different brands of the same exact thing, same information. Oh, Alvaro, thank you. All right, good, cool. Hey, Matt. I've seen you in some of our classes. Thank you for attending as well from Seattle. Excellent. Thank you very much. All right, we've wiped the board. Thank you very much. I'm glad we could have this time. And I would like to thank everybody for taking some time out of your week to come join us and hopefully learn a little bit more about CAN and network diagnostics. Krista, do you have any closing words for us?
I do. Thank you, Jason, for this very in-depth look at vehicle networks and diagnostic testing strategies. And, to echo what Jason said, thank you to our viewers. This presentation will be available in archive and to rewatch or share with others. So again, on behalf of Motor Age, PTEN, and Snap-on, we appreciate you taking time to watch. Have a great night.
Thank you very much.